In this video, we're going to cover the topics of concavity and the second derivative test. We're going to start with concavity first by defining it, and we're going to break it into two parts. So the first part says a graph is concave up when f prime of x is increasing. Okay, so let's think about what that means. In this context, f prime of x we often think of as the slope of the function. And so if the slope is, I said increasing, didn't I? Let's try that again. There we go. If the slope is increasing, that means it's becoming more and more positive. So what does this look like graphically? So the most common way we see concave up is with the upwards opening parabola. And we have this property described here because on the left side, as we go down to the right, these are negative slopes getting less negative till we reach a zero slope, and then the slopes continue to get more and more positive from there. So this is an example of concave up, and I'll use this abbreviation for that throughout today's video. And of course, the other one we're going to consider is when a graph is concave down, and that occurs when f prime of x is, of course, decreasing. Okay, so again, we're thinking the same thing. So this time, we're still thinking of the first derivative as the slope of this graph. And if it's decreasing, then the slope is getting more and more negative. Okay. So visually, we're thinking of it as kind of like an upside down bowl or cup. I like to think of cups since concavity with a C. Anyways, and the reason this works is because we start out with positive slopes as we move to the left. They become less positive, eventually zero, and then they become more and more negative. Okay? So this is an example of a concave down, or it's like a cup turned upside down type of function. And so today we're also going to be working, obviously, with the second derivative a lot. And so we can describe these things using the second derivative. So for instance, when we're talking about f prime increasing, this was like when we talked about velocity increasing, and that occurs when the acceleration is positive, or in a more general sense, this occurs when the second derivative is positive. Okay? And then similarly, if our slope is decreasing, that means the second derivative, or how the slope is changing, is negative. Okay? So this video is focusing on the second derivative. This is how we use the second derivative to identify when a graph is concave up versus concave down. We look for when it's positive versus negative. Okay? So the next kind of definition we have to go through here is what's called a point of inflection. Sorry, my pen really doesn't like eyes right now. Oh, there we go. Okay. Which we abbreviate POI in a lot of cases. And that is where the function changes concavity. Okay? And so this would occur wherever the second derivative is 0 or undefined. So that's a common thing we look for in this unit. Because that's where it's switching from either concave up to concave down. So the second derivative switches from positive to negative, or vice versa. So to do that, it has to either cross through 0 or be undefined. Okay, so that's a vocab word. So we had our critical points, and now we have our points of inflection. And they're two different things. We got to keep it straight. So let's do some quick pictures here to kind of think of some scenarios and just get a general sense. So the most common way we think of concavity is just kind of like, I guess it's a more obvious way, but and in this case, the point of inflection is where it's switching. So it's switching from an upside down cup, which would be concave down, to a cup that's opening up. And where it's changing is right here at the point of inflection. So that's our point of inflection for this graph. Okay, so it doesn't have to be a full cup shape for it to be concave up or concave down. So this is the easiest kind because it's almost a complete version of each type. Often they're not full cups, so to speak. So another one could look like this. Might be a little exaggerated there in the middle. But the first part of this graph is kind of like half of an upside down cup. So it starts out concave down, and then somewhere around here at this point of inflection, it switches to a right side up cup shape, or concave up. Okay. Another way you might see it looks kind of similar to this, but instead of going flat in the center, the kind where it's kind of a vertical S shape, and I'm not great at drawing these, so bear with me. So it's like if we had a more of a this type of curve. Okay, so again, it starts out kind of opening up, and then it switches here to concave down. Okay, so those are some basic examples you'll come across. Then there's the kinds that don't have any points of inflection, or just types of concavities that might not, again, be that whole entire shape we're used to seeing. So for instance, if you have a function like this that's always increasing, we can tell that this one is concave up, and it has no point of inflection, right? It's just staying concave up. Another way that might show up is going in a decreasing motion. Okay, so these are both examples of concave up with no inflection points, where it's not changing concavity. And then, of course, the same can be true for concave down. So sometimes we have something like this. And sometimes we have something like this. Okay, I guess it probably would have made sense to flip-flop these. Sorry, I get too OCD about this. So concave down, but increasing, would look like this. And then concave down, but decreasing, would look like that. There. That makes me happier. Okay, so here's how concave up can increase over the entire function, concave down, and then decrease and decrease. And these have no points of inflection.